Hi guys, welcome to microwave engineering course. As the first lecture of the course, I will briefly introduce microwave engineering and histories and background. So first of all, this is my information. My name is Sangjo Choi, and I'm in 527 office. And you can check my information. And basically, if you have interest in the EM courses and microwave engineering, it is welcome to discuss about your study and career in this field. And about microwave engineering, you guys learn EM 1 and 2. So at the end of EM 2 course, you guys learn Maxwell's equations and wave propagation. In the first semester of third year, you guys, some of students learned wave propagation, transmission line, and antennas. So from this semester in microwave engineering, we will touch transmission lines again and move on to Smith chart and so on. So you guys don't worry about that you didn't take EM field course. So I can review EM and then transmission line and move on in microwave engineering course. So in the course, we will use microwave engineering book written by Professor Pozar. This is the most famous book in microwave engineering field. In terms of grading, midterm and final exam will cover 40% individually, and homework 10% and quiz is 10%. So in my course, students need to can solve homework problem by themselves, and if you guys do that, you will get a good grade in exam. So you need to work kind of daily base, not just on the exam period. My course. So let's move on to the history about Maxwell's microwave engineering. So the basic equation we use in microwave engineering is Maxwell's equation. So you guys learn from EM2 courses and EM field courses. So these four equations explain all the electric field and magnetic field phenomena in nature, right? So the first one is about electric field, right? Divergence of D. D is electric field flux intensity. So that means the electric field flux generated from this charge, right? This plus charge. If we have minus charge, the electric field is converged, right? This is diverged, this is converged. So this is about first law. And then about second law, divergence of B is 0, which means we don't have this plus and minus magnetic charges, right? So if we think about the magnet, right? Magnet always have N and S at the same time. So magnetic field generated and ends in this NS combination, right? Not just only N, right? So we cannot make magnetic field from N magnet like this, right? So this is H field or B. So about third equation, simply, right? B changes, right? Magnetic field change in time can generate electric field, right? So this is discovered by Faraday's law of Faraday. And Faraday, right, in experiments proved that when we change, so if we have a wire loop, right, and if we change the magnetic field inside the loop, right, if we change the position of magnet in terms of this wire, as we change this and magnet, Faraday observed the current is generated in the loop, right? So as B changes, magnetic field changes, he found that electric field currents can be generated, right? This is Faraday's law. So about fourth one is opposite of this Faraday's law, right? So as we change electric field, we can generate H, right? So this is the term the Maxwell's added in the Maxwell's equation, right? This is displacement current. Right? So Maxwell is a mathematician, right? He's not experimental physicist, so he's really good at math. So if we take a look third and fourth equation, right? So we need to have some term similar to this so that it can be symmetric, right? So he added these terms, and then if we use this term, right, then we can solve wave equation. We can find wave equation. Then we can finally get electromagnetic wave, EM wave. All right, so we did that. So wave equation, by solving wave equation, we can get EM wave, so electromagnetic wave, right? So electromagnetic wave is propagate maybe to this direction, and electric field, if we have electric field like this, propagating to this direction, and magnetic field is it's coupled, right? Electric field is this direction, electric field have this component, and magnetic field should have this component, perpendicular to each other. And the E and H has some ratio, right? So E and H ratio is intrinsic impedance, about 377 in air. And then what he found is that, so he got the wave, right, through the mathematics. And what he found is that the velocity of the EM wave is same as velocity of the wave. Propagation velocity is calculated like this from the equation. This is happen to be same as C, right? Light velocity, 3 times 10 to the 8 millimeter per second, right? So he found that, oh, this electromagnetic wave, right, is related to electric field, and magnetic field is propagating in the light velocity, right? And then he just think that light is also electromagnetic wave, right? So this is what he found, and then he predicted that electromagnetic field, electromagnetic wave in mathematics. So at that time, people didn't accept this kind of prediction, because that means in the air, right? In the air, no medium. The air is medium, but at that time, people think that it is nothing, right? Nothing, but some information is kind of propagate. So that kind of concept was not accepted before Hertz. So in about 15 years later, Hertz, in German, a scientist, proved that EM wave can be generated from this antenna, and then this is a receiver. So basically what he did is, from this kind of transformer, he excited very high voltage to this antenna. This is antenna. So a spark is generated. And when this spark generated, EM wave is propagate, and then this receiver side, with the ring side, he found that the spark in the receiver side. So between this transmission side, TX transmission side, and receiver side, nothing, right? It's kind of just air, right? But he proved that the spark is transferred from TX transmission to receiver. So this spark is very weak, so that he need to make the room very dark with nothing, no light. So So with this kind of situation, he observed the spark is transferred from the TX antenna. So this is experimental proof of EM wave, and then Hertz didn't know about the good thing about this EM wave, but this experiment inspired wire communication. So after that, the first commercial device which used the wireless kind of signal EM wave is wireless telegraphy. So this device was invented by Marconi in England. So as I said, right, Hertz should make the room very, very dark to see the received signal, right, spark. But instead of that, he used this device so that when we touch in TX side, if we touch something, then this RX side, this detector provides some sound. So we can make sound very short and long so that we can make some code, right? So he used Morse code to kind of to deliver the message in alphabet. So this is dot, small one is dot, this is dash, right? So with this sound, they can communicate, right? So they use the sound as a detection of the signal, right? Spark, from spark to sound. So this is code based, right? So we call it wireless telegraphy. And then after this, people try to send voice through the wireless medium. So AM, amplitude modulation, a radio was invented after this telegraphy. so very simple explanation about AM is, so let's say we have voice signal, right? Voice signal changes in time, and the voice signal is about near 1 kilohertz signal, very low frequency. And then if we convert that to wavelengths, lambda is about 300 kilometer, very, very long, right? And then in terms of antenna length should be lambda divided by 2, so that the antenna size should be 150 kilometer, right? So which is very big, right? But to send this signal, we multiply with carrier signal, which is a much higher frequency, about 1 gigahertz, right? So this is 10 to the 9 hertz. This is 1000 hertz, right? So much higher frequency we mix together so that we will have this amplitude modulated signal. So this voice signal is still there, but the mix with this carrier signal. So the good thing about this kind of modulation is that we can increase the frequency of this signal, right? So it's near 1 gigahertz. So with this, the antenna size become very, very small, right? So 1 gigahertz wavelength is about 30 centimeter. So that antenna size can be 15 centimeter, right? So compared to the 150 kilometer, 15 centimeter is much smaller, right? So antenna can be smaller so that we can efficiently kind of design the antenna so that we can realize the communication between transmission and receiver. So this is a transmission block diagram. So this is the mixing circuit with this input, and this is high frequency. So we generate a modulated signal, and then with this amplifier we amplify the signal, and then we filter the noise, and then we send the signal through the antenna. So this is transmitter side. All right, and then so the EM signal will be transmit through transmitter, and then what we need to do, we need to recover the data, right? So the voice signal, right? So how can it detect? So you guys learn envelope detector from electronic courses. So simply they use envelope detector. So using this one, right, with diode and capacitor in the register, you can track the envelope of this signal, so that this detector can recover the signal. So this step we call a modulation, right? Modulation. And then this is demodulation. So we kind of recover the original signal, right? So voice, so that we can listen to the voice which is generated from the far side, from the transmitter. So this is kind of basic explanation about communication using AM. So nowadays, you guys use a cell phone and LTE and Wi-Fi protocol for the communication. So we use digital or wireless communication. So we start from the voice signal, which is continuous signal, but we sample the data, right? So using this sampling process, we can make digital signal, right? So this is the block diagram of a analog. This is analog to digital converter, and then this digital signal. Nowadays we use digital modulation schemes such as PPSK and QPSK. So I don't cover this one. You guys will learn from communication courses. So using this modulation scheme, you guys can enjoy your kind of YouTube, and you can also kind of talk on the phone on through LTE communication, right? So I've discussed about communication system. So why I discuss about that is I want to distinguish two things. So so this is transmission side, this is receiver side, right? So transmission side is send the signal, and receiver side is receive the signal, right? So this modulator, right? Modulator, just simply say, we just say 1 kilohertz signal, right? Kind of just don't think about voice signal, right? And then if we mix some high frequency about 1 gigahertz, so in this red box we'll have the signal will near 1 gigahertz signal, right? So much higher frequency than this modulator size, right? So in microwave engineering, we are interested in these red boxes. So circuit or line which is working at high frequencies such as a gigahertz or 100 megahertz. So in transmission side, so there's filter and amplifier. So we amplify the signal which is generated from the voice and then send it to receiver side, and then receiver side get the signal from the antenna. And basically switch means when this transmission is working, this switch is connected to the TX side. When this device is working as receiver mode, right? So you guys watch the YouTube, right? Downloading some data, you guys use receiver mode in your cell phone. So in receiver mode, some signal generated from the base station signal coming here, and then we amplify the received signal through LNA. This is a low noise amplifier. So basically we amplify the wanted, the desired signal, and then filter out undesired signal, and then mix and then make the frequency to 1 kilohertz. So in this region, we are dealing with 1 gigahertz signal, right? So if you see this block diagram, all the switch and LNA or filter or mixers are connected through this line. So this line looks simple, but in microwave engineering with this high frequency, we need to carefully design this. So we call this is transmission line, and then between these components, the signal will be transmitted and deflected. So reflection between components is also important topic in this microwave engineering. And network analysis means we model this component as network. So to study this component, we need to know network analysis. So in the passive component in this red box, include antenna and filter. Passive means it doesn't require bias, DC bias. Basically, so no transistor, no diode, right? So active components basically amplifier, power amplifier in this transmitter side and the LNA, low noise amplifier in receiver side, and the mixer is also use transistor and diode. So basically need DC bias, right? So this is the component we use in the microwave engineering, and we design in the cell phone circuit. So in terms of spectrum frequency range, the important band frequency that we need to know is about RF frequency and microwave frequency. So you guys learn microwave engineering, right? And the people say, what is a microwave engineering, right? The microwave engineering is about some EM wave with high frequency. So what frequency? Then you can answer like RF frequency, radio frequency is about 3 megahertz to 3 gigahertz. So if we convert that to wavelengths, right, it's about meter or some 100 centimeter, right? So this is similar to a TV or radio. So we call that radio frequency. And sometimes we call 3 to 30 megahertz also radio frequency. But approximately you can in definition you can say radio frequency from 30 megahertz to 3 gigahertz. And then second one is microwave frequency. We can understand this range from 3 gigahertz to 30 gigahertz. So this is basically from radar. Radar means the detector, right? So we use automobile car radar to detect the car in front of your car. So in the conventionally radar system use 3 gigahertz and 30 gigahertz. So this is microwave frequency definition come from this radar system. So basically 3 to 30 gigahertz means centimeter wavelengths, 1 to 10 centimeter. And above that is 30 gigahertz and 300 gigahertz. We call millimeter wave. So wavelengths become millimeter, so that we call that 30 to 300 gigahertz is millimeter wave. So 1 centimeter is about 10 millimeter, right? 10 millimeter to 1 millimeter. So we call that millimeter wave. So this slide is from the textbook. So we have similar definition. So you don't need to worry about all the numbers, but you have some picture. I mean, just a brief understanding of RF and microwave engineering. microwave frequency. And then and also important spectrum is millimeter wave nowadays, right? So I said 30 gigahertz to 300 gigahertz is millimeter wave frequency, but nowadays, right, for 5G, people consider 28 gigahertz as the ideal spectrum. So 28 gigahertz, even though smaller than 30 gigahertz, we call millimeter wave communication. So this is in terms of cell phone industry. And beyond 5G, right? So people also consider 6G frequency. So 6G frequency basically over 100 gigahertz. So this is an interesting topic and for research and device development. So and then if you see a little bit more about the spectrum, so you will be familiar with FM, right? FM signal. FM is about 80 or 100 megahertz, right? And then cell phone, right? Cell phone, actually GSM in the US use about 800 megahertz, right? So, and then LTE, we use up to 5 gigahertz, right? Then sub 6 gigahertz. So 800 megahertz to 5 gigahertz band. So LTE use very wide frequency band. Even though the band is very small, but LTE use quite a large bandwidth of this spectrum from these frequencies. And GPS, right? You guys use navigation for this using this GPA, so the frequency is 1.5 to 1.2. And then in the kitchen we use microwave oven, right? So it uses 2.4 gigahertz. So this is also related to RF and microwave frequencies. So why do we study microwave engineering? So from the background, I kind of explain a little bit about that. But compared to the standard circuit theory, right? You guys learn circuit theory from second year. You guys studied DC signal and the AC signal and RLC. But that circuit theory is covering DC or kilohertz, very low frequencies, right? And then you guys model circuit as RLC, right? Discrete circuit. If we have some resistor, so you guys represent as this R, right? That's it. But if we move on to the microwave circuit theory, this theory doesn't work because the signal is 100 megahertz or dozens of megahertz and gigahertz, right? So why is it different, right? Why this higher frequency change the circuit theory, right? So the thing is, as frequency goes up, right, wavelengths become smaller, right? So from the Maxwell's equation, right, we learned that C, right? So this is velocity, so meter per second. So in the wave, meter is related to the wavelength, second is related to period, right? So frequency is 1 over t, so this is lambda f. So lambda f is c, right? So as frequency, if we change it like this, as frequency goes up, lambda becomes smaller, right? Lambda becomes smaller, right? So if we have some 10 centimeter wire, so if we have kilohertz, right? So the wavelength is about kilometer, right? So if we excite some AC signal, it will be almost kind of stable, right? But if we use maybe 10 gigahertz signal, wavelength is about 3 centimeter. So it will change like abruptly along this 10 centimeter wire, right? So we cannot. So each point has different voltage and current, right? So that we need to kind of divide this wire very small, right? Let's say delta L, right? So we represent this small portion with this distributed circuit. So basically in microwave circuit theory, we should use distributed circuit and not discrete circuit. So this is big difference. And if we compare electromagnetic theory and microwave circuit theory, so you guys learn EDHB, right? Electric fields intensity, electric field intensity and flux, and magnetic flux and intensity, and then this was vector, right? And then we use differential and integral equation, and then del and curve. So it's kind of a little bit complicated and then hard to accept at the first time. But in microwave circuit theory, so it's a circuit, right? So we use voltage and current, so impedance. So this is all scalar, right? So that I expect this microwave circuit theory will be easier compared to the EM theory because we use scalar values. And then so why microwave engineering is good, right? So and then the difference is that microwave engineering utilize high frequency. So why do we use high frequency? Why do we need to use it? So because high frequency can provide wire bandwidth. So the reason why we use 5G and 6G, because we want to increase the frequency, right? So that we can achieve wire bandwidth for higher bit per second, right? Data rate, right? So if we imagine 600 megahertz, right? 1% means 6 megahertz. So BPSK means digital communication modulation. So you don't need to worry about it, but just this modulation provides 1 megahertz to 1 bit per second. So basically, if we have more megahertz, we will have more BPS, right? So 1 megahertz means 1 mega BPS, right? So 6 megahertz means 6 mega BPS, right? But if we use 6 gigahertz, and then even though we have a same percentage fractional bandwidth, we will have much higher bandwidth, right? And the data rate will be 100 times higher. So this is benefit of high frequency in the microwave engineering. And then as this frequency goes up, wavelengths become smaller, right? So as wavelength smaller, radar can detect smaller target. And then smaller wavelengths means antenna length, right? It's about lambda divided by 2, can be also smaller, right? So that we can implement more antennas in the device. So the antenna performance can be better. And then the last thing is about line of sight. So this is discussing about the ionosphere from the Earth. So we have GPS communication, right? So navigation system is utilize this GPS signal from the satellite. So let's say we have satellite and then we have Earth, right? In between we have an ionosphere. So this material between the satellite and Earth block very low frequency. So that we should use high frequency. So we use 1.2 gigahertz or 1.5 gigahertz. for this GPS communication. So this is GPS system, navigation system is another application of microwave engineering. So that we can understand that microwave engineering can be used wireless communication, right? LTE, 5G, and then Wi-Fi, right? WLAN, and satellite communication, and also radar. So if you take a look at your cell phone, but you cannot see this one in the outside of the cell phone, but inside you have an antenna to receive LTE signal and Wi-Fi signal. So this is antenna implemented in your cell phone. So this is about EM theory, right? And then in terms of microwave engineering, right, we have this kind of PCB board inside the cell phone. And then if you take this green box, you will have this chip inside. So I show you the antenna for the microwave engineering communication circuit. So we have amplifier, filter, we have switch, amplifier, filter, and mixer. This is for TX and RX. We have LNA or filter. So filter can be in here or there. So it is depending on the application. So we basically have filter and amplifier, right? So this kind of block diagram. So we normally design this before the mixer. So power amplifier, low noise amplifier, and filters are implemented in the chip. So this power amplifier, low noise amplifier, this is filter. And in between we have inductor and capacitor. So this is used in between the component to make this signal flow is efficiently. So this size is about your fingertip size, very small size, and then mounted in your cell phone so that it can transmit and receive the RF microwave signal for LTE communication. So this is the real 3D model for this circuit, this chip, right? So using this kind of model or simulation tool, we can design this very complicated microwave LTE chip inside of cell phone. So from this review, I think you guys maybe have a glimpse of this microwave engineering, including all the components and transmission line. So this one will be covered so that you guys understand basic of this microwave engineering, then RF circuit. So this is application microwave engineering. So I think I already discussed or explained enough so that you guys can take a look this YouTube video so that this microwave engineering can be used for cellular communication, right? 5G or LTE, and then this is for car radar. So all the car have radar which detect the car in front of your car, right? And then that radar use electromagnetic wave. It transmits electromagnetic wave to the target, and then the reflected wave is detected through this radar. This is the third one is the wireless power transfer. Transfer. So wireless communication deliver the information, right? Data. But this power transmission is transmit the power to the receiver without any medium, right? So this can be used for the car, electric car charge. So So this is also a very useful technique which utilize microwave engineering. So you can watch the YouTube video. So this is antenna implemented in the 5G cell phone so that we can receive 5G 28 gigahertz signal efficiently. So this is technique which is implemented in the semiconductor chip so that the size can be smaller and then implemented in the cell phone, right? Very compact form. And this is the radar system implemented in the automotive car. So this utilize about 70 gigahertz signal, very high frequency to detect radar. So the reason why we use high frequency because we want to detect very small object, right? In the car, you see this kind of shark shape or shark fin antenna is used for the communication. This so for the military application, so this radar in the airplane is also used, right? So this is another application of the microwave engineering. So this is plan. So you guys can take a look, and then that's it for today. So let's move on to the EM and fundamental of EM in the next class. Right, see you next time.